If somehow the laws of physics changed so that there was no magnetism, I mean, all bets are off, and God knows what the world would be like. Really and truly, it would be so profoundly different that you couldn't say that, oh, well, we wouldn't have cars or anything so trivial as that. We wouldn't have light. Light, the first thing mentioned in the Bible. Number one, God separated the darkness from the light.
Since the first moments of creation, magnetism has been a force in our universe so powerful, so fundamental, nothing in our world would exist without it, not even us. In the beginning, humans first discovered magnetism as a small miracle, a dark stone that attracted iron with an invisible force. In a time when fire was tamed to fashion tools, when the stars were all named, here was something truly magical. A rock with a mind of its own. It was an effect without a cause.
When science began, it began in the Greek colony of Miletus, 650 BC on a Thursday morning, or something like that. People started saying, look, let's look for a logical explanation for this complex world. And lodestones were part of this curious complexity.
Lodestone is an iron ore, a natural magnet. The Greeks found deposits of it in the province of Magnesia, and that's how magnets got their name. Hippocrates, while he was busy inventing medicine, thought a thing as curious as lodestone must be good for something, so he claimed it had healing powers. By the Middle Ages, lodestone was believed to increase elegance and charm and restore marital harmony. People believed it cured everything from heart disease to gout. Mariners told tales of ships sunk when lodestone mountains pulled all the nails from their hulls. By 1269, Petrus Peregrinus began to explain the magic.
Ta-da!
He reported that all lodestone, if allowed to rotate freely, pointed in the same direction.
Rock. This rock has some very, very special properties. It does turn, that's true.
Peregrinus also demonstrated that the rock could transfer its magnetic power to an ordinary iron needle.
You could hang it up on the deck. Sailors were going to sail north.
Travelers no longer had to depend on the sun and stars to guide them. Magnetize a piece of iron, float it or mount it on a pivot, and you have a compass. Ready to guide a Sunday sailor around the bay or Columbus to the New World.
The stone disclosed to Flavio its secret love for the pole, but he disclosed it to the sailor.
In 1600, William Gilbert's revolutionary treatise on the magnet disclosed that pounding hot iron induces magnetism in the metal. He also reported that a magnetized needle, when floated in water, not only pointed north, but also slanted down, towards the earth. The needle seemed to be reaching for something. For Gilbert, this meant the earth had a magnetic soul. He was right. The earth itself is a giant magnet. Researchers today believe that magnetism comes from currents in the liquid metals in the earth's core, but there are still as many questions as answers. We do know that magnets come in all sizes, as large as a world, as small as an atom.
Today we know that the origins of all magnetism are in the atom. And it comes from the way the world works. The way the world works is the atom consists of electrical charges. They have names, the electron and the nucleus. That's essentially the two parts of the atom. And the nucleus is tiny little small things sort of floating in the middle of a giant volume in which electrons whiz around. Now, if you have an electric charge that's moving, you create a magnetic field. But if these magnets are misaligned, so that here's a North Pole and a South Pole, and there's a North Pole and a South Pole, and they're all every which way, then the net effect is zero magnetism, and that's what most substances are. They have no magnetism.
But in some metals like iron, clumps of atoms line up and point their poles in the same direction. These clumps are called domains.
And suddenly you have an accumulation of all North Poles on one side, all South Poles on the other side, and you have a bar magnet.
A little bit more. Oh, look at that. You can put a little bit more. And then
Sprinkle iron filings over a bar magnet and you can see magnetism.
What is happening as he drops them?
The magnetic field is not uniform. It has invisible magnetic lines looping out of the top and bottom of the magnet.
Look at those beautiful magnetic lines of force.
The Earth is a little large, but if you could surround it with iron dust, you'd see the same loops of magnetic force. Like all magnets, the Earth's field lines converge at its magnetic poles. It is this field that protects us from cosmic radiation.
The sun, being a big, powerful star, is constantly ejecting a rather powerful stream of charged particles that fly through space. And were they to hit the planet Earth, the radiation that they caused could damage us, could give us skin cancer, cataracts. The Earth's magnetic field channels those charged particles and acts as a barrier to prevent them from striking the atmosphere. However, the Earth's field dives in to the atmosphere at the North Pole and the South Pole. When those charged particles hit the atmosphere, they ionize it, they make a weak plasma like we see here.
Plasma, a superheated gas in which electrons are stripped from their nuclei.
And it's those sheets of plasma that you see, that rippling, beautiful light that we call the Northern Lights.
These curtains of light lived in the legends of the people of the North. The Inuit in Alaska thought the aurora borealis signified celestial battles. 16th century Germans believed the sky was on fire. To the Chukchi people of Siberia, the souls of their dead lived on in the light. Even today, the northern lights have the power to capture the human imagination. The magnetic forces that shape the glow in the sky can also be used to push products. Far to the south, in the heat of California's Death Valley, the history of the Earth's magnetic field is locked in layers of rock. When rock forms, some of its magnetic particles line up with the planetary magnetic field. By cutting samples from the different layers of stone, researchers can show the Earth has had the same magnetic alignment for 700,000 years. But hit a layer lower than that, and the rocks reveal that there have been times when compass needles would not have pointed north.
And one of the strangest things in geomagnetism is the magnetic reversal. The idea that the entire planetary magnetic field can come discoupled from the rotational axis. Instead of pointing north, the magnetic field might be pointing east for a while, and then reestablish itself, and your compass needle will point south.
Death Valley is an ideal place to learn about magnetic reversals.
There's an active fault zone that runs through the bottom of Death Valley here. It has taken these lake beds, turned them on end, thrust them up, and then the streams have dissected down through them, so we have almost 100% exposure. It's one of the few places where we can go and say, right, the magnetic field started in a normally magnetized state here, and 3 or 4 meters up there, it's in a discretely reversed state. And yet what we're recording is the history of the Earth's field. Each little bed, when it is formed, preserves precisely the magnetic field at the time.
Core samples are analyzed in a magnetometer to determine the strength and direction of the magnetic field. Researchers can use that information to plot a geomagnetic map that tells the history of the Earth's field reversals. Far from Death Valley, there are other reliable places to study geomagnetism. Volcanoes. Molten magma erupting from the Earth's inner chambers is rich in iron. When it cools, it locks in clues not just about the Earth's magnetic field, but also about how the continents were formed.
And so if I have a liquid magma that comes up and then gets in place, solidifies, and then cools, those grains become magnetic. But the important thing is, as they become magnetic, they lock in their magnetic direction parallel to the Earth's field at the time.
Beneath the surface of the ocean, cooling lava locks in magnetic information as it creates new seafloor. Over millions of years, a stripe pattern forms, creating a timeline of the Earth's field reversals. These patterns tell geologists that as new stripes form, the continents are pushed apart. This observation led to a major breakthrough in understanding the way the Earth works, the theory of plate tectonics.
There's no parallel in the history of science where one set of observations made such a key change in the entire field and turned everything. Perhaps the only one that's comparable, say, is the Darwinian revolution in biology, which still has its ramifications. But the plate tectonic revolution was a similar thing in geology, and that was driven by magnetism.
Whether on the sea floor or in Death Valley, magnetic stripes also hold clues about when the Earth's field might reverse again. Studies indicate we are in a period when the magnetic field is declining fast, 15% since the year 1670. If the present trend continues, the Earth could lose its entire magnetic field in about 2,000 years. Compasses would be useless, the northern lights would vanish, and our globe would be exposed to cosmic radiation. But no one can be sure if this will happen. The magnetic field could also reverse its trend and begin gaining strength, keeping intact the magnetic world we've come to depend on. If you look at our fellow inhabitants on Earth, they seem to know where they're going. But how do they know? Biomagnetism may be the answer.
Well, there's been speculation for a long time about the Earth's magnetic field providing a cue that could be used by organisms, especially after humans were able to use the magnetic compass as a navigational aid. People speculated, well, the Earth's magnetic field could also provide a cue to other organisms in navigating their way through the world.
The mystery of how animals can navigate is a big problem in sensory biology. How does an animal know to do that? And various groups of biologists have studied this, and it turns out you discover that animals are extremely clever. Pigeons, for example, can hear sounds both higher and lower frequencies than humans do. They can hear bridge vibrations in New York, in home on it. They can see polarized light patterns in the sky. They have a sun compass.
But as wartime messengers, pigeons headed home without sunlight and bridges to guide them. There had to be another technique the birds were using to find their way. The answer came on a cloudy day in 1974 when Cornell University researchers attached magnets to pigeons' heads. Birds that normally flew directly home became hopelessly disoriented. Findings that pigeons can use magnetism to navigate prompted new studies in animal migration.
One of the most intriguing aspects of all of this work is simply that you have a large number of very simple animals that evidently have evolved the ability to perceive something that we ourselves cannot see.
It is late autumn, and off the coast of Florida, spiny lobsters are on the move. Their only chance at survival is to reach the warmer, calmer depths before winter.
They're able to hold their courses despite the fact that they often migrate at night. They often migrate when a tremendous amount of sediment is suspended in the water so that visibility is rather poor. And they're able to migrate under conditions in which waves and water currents are impinging upon them from different directions.
To find out if lobsters have a magnetic sense, Ken Lohman set up a tank where he can control the magnetic field. Once in the tank, the lobster on a leash orients itself based on the existing field in the tank.
All going, so we just have to wait for the lobster now.
This is a north-seeking lobster.
All right, we'll change the field in 5 seconds.
Nothing diverts the creature from its course until the direction of the magnetic field is reversed.
Our results from the laboratory experiments demonstrate that lobsters have the ability to orient by sensing the Earth's magnetic field. This suggests that they may be able to guide their migration by detecting the Earth's magnetic field.
Out of Ken Lohman's clutches, the lobsters do what they ought to do, a migratory dance along magnetic lines of force. The ability to detect magnetic fields goes beyond pigeons and lobsters. Scores of animals seem to be sensitive to magnetism. This sixth sense might be traced to small grains of lodestone or magnetite found in animals' brains. The question is, how small can you go and still find biomagnetism? Richard Frankel collects bacteria from saltwater marshes on the California coast to study their magnetic properties. These bacteria have a problem. They seek food and security in the muck under the pools of water, but they don't have eyes to guide them, and they are so tiny they're unaffected by gravity. The bacteria may be simple single-celled creatures, but they navigate the same way Columbus did.
Looking at the monitor here, we can see bacteria swimming out of the sediment particles and accumulating at the edge of the drop, which is closest to the yellow end of this bar magnet. And now after they've accumulated for a while, I can show you that if I turn the bar magnet around, the bacteria swim away from the drop.
Unlike the pigeons and lobsters, we can actually see the bacteria's internal direction finder. This is a picture from an electron microscope, the organism magnified 100,000 times. The bacterium is a living bar magnet.
Well, what the bacteria did, or what they do, in fact, they're doing it right now out here, is they make these single domain-sized particles of magnetite, and they line them up in a chain. And this forms a permanent compass needle that is just large enough so that the bacterium is oriented in the Earth's magnetic field as it swims.
But are the bacteria actually heading north? Not really. They're swimming down to where the food is. It works just like the floating needle experiment.
If this is the north-seeking end of my internal compass needle, if my flagellum is back here, if I just start swimming straight ahead, then the Earth's field will align me in a particular direction and I'll swim down to the sediments. When you look at these bacteria, you see this chain of particles looking very much like a backbone running through the cell. And in fact, there's an interesting correspondence between the fact that bacteria can mineralize, can produce an internal mineral. I mean, that's what we do. That's what bones and teeth are.
It's kind of an amusing idea, but it could well be that this skeletal system that we now have in our cells evolved in these magnetic bacteria to keep these magnets in line. And if that were the case, that's kind of an absurd conclusion that perhaps we wouldn't be here if it weren't for the magnetic field driving the evolution of this.
If we have magnetic microbes to thank for our spines, is it possible that we too have internal compasses? When he's not digging in Death Valley, Joe Kirschvink is busy in his lab dissecting human brain tissue, looking for magnetite. He finds it, miniature magnets among the neurons.
The discovery of a permanently magnetic material in human tissues is a surprise. I mean, if I take a magnet, it doesn't normally stick to my head or to my fingers, and the assumption was that there's probably nothing ferromagnetic there. But it turns out nobody had looked.
What Kirschvink did was turn his tissue samples into a kind of brain soup. A strong magnet placed in the liquid pulled iron oxide crystals out of suspension.
What we know at the moment is that all of the crystals that we've seen and extracted and purified and studied are perfect biological bar magnets.
The crystals in our brains are almost identical to those in the bacteria.
If you realize that birds and fish and other vertebrates, our cousins evolutionarily, also produce this material, shouldn't be that much of a surprise that we do it as well. It's our ancestors anyway.
So we've got magnets in our brains, but there don't seem to be enough of them to serve any purpose in human beings.
Perhaps at a distant point in our evolutionary past, the ability to sense the Earth's magnetic field was extremely important to us, and its importance may have diminished over time as our other sensory systems became more and more sophisticated.
Human magnetism may be more useful as a conversational metaphor than as a direction finder. We talk about people having a magnetic personality. Some people we find attractive. Some we find repulsive. Those with major differences we call poles apart.
Attraction and repulsion, reason and energy, love and hate are necessary to human existence.
In the late 1700s, Franz Anton Mesmer proposed the existence of a force called animal magnetism. To him, it was more than a metaphor.
And his theory was that there was some kind of a fluid that flowed from the Earth's poles through the human poles and so forth. And so if that flow was unblocked, that constituted health. But if you got blocked somehow, then you got sick. And his therapy was to rub people with magnets.
He had one subject swallow a concoction containing iron before attaching magnets to different parts of her body. She reported feeling streams of a mysterious fluid running through her veins. Mesmer also hosted what he termed therapeutic seances. At one, patients sat around a vat of sulfuric acid while holding on to iron bars. They were mesmerized. Though declared a charlatan and a quack by a royal commission, Mesmer had started something, the magnetic link between magic and medicine. Years later came a device that actually put magnetism to work for medicine. Magnetic resonance imaging revolutionized healthcare, and the acronym MRI entered the popular lexicon. A patient is bathed in a magnetic field 5,000 times stronger than the Earth's. This field causes some of the body's nuclei to behave like spinning compass needles and line up. Then, the nuclei are hit by pulsing radio waves. Once the pulses stop, the nuclei drop back to their original state induced by the magnet. The energy released acts like miniature radio station signals. These signals are delivered to a computer where they are translated into an image. MRI images save lives by detecting life-threatening cancers like this brain tumor earlier and more safely than other imaging techniques like X-ray.
Magnetism has really opened up a new sense of the sixth sense. We could call it a seventh sense, which we've had to create with these large magnets and all the technology we've developed. So I think it's really given us a whole new insight into the body, and we're just still scratching the surface as far as how much this new sense and this new information can provide us about the functioning of our bodies and life in general.
This magnetic machine provides more than static pictures of the body's structures. By taking several images in a row, scientists like Bob Balaban make movies of human thought.
Then we'll ask you to hold your thumb down.
After placing a patient's thumb on a hot plate, Balaban uses the MRI to chart areas of the brain reacting to pain. Scientists are also using fast MRI to study cerebral maladies like epilepsy and schizophrenia. Whether detecting cancer or analyzing thought, MRI provides a magnetic window into once hidden realms of the human body. magnetism is more than an invisible force protecting the Earth and guiding its inhabitants. Together with electricity, magnetism ignited the machine age and created the modern world.
Electricity and magnetism are used to make motors run, to make videotapes work. They're used in our cars and our stereos. They're part of our world. If you choose not to know about something like that, then it becomes magic.
Understanding what seemed to be the magical link between electricity and magnetism began with an observation. When ships are hit by lightning, compasses on board swing wildly. In 1820, a Dane named Hans Christian Ørsted recreated this natural phenomenon in his laboratory. He placed a compass near a wire attached to a battery. As the electric current flowed through the wire, the compass needle kicked. Ørsted had shown that an electric current generates a magnetic field. In England, Michael Faraday took Ørsted's work a giant step further. His 40-year study of electromagnetism would bring about a technical revolution. First, Faraday showed that a wire placed next to a magnet rotates when an electric current flows through the wire. That was the beginning of the electric motor.
We got it.
You got it?
Yeah.
We have a motor.
Years later, Faraday made his second discovery. He found that moving a magnet in and out of a coil of wire creates an electric current in the wire. That was the beginning of the electric generator. Now mechanical energy could be converted into electrical energy, and electrical energy into mechanical energy. A new world dawned. The parade began.
Magnetism, the poor old workhorse, just keeps going along. Magnetism is involved in motors and all kinds of machinery. It's involved in electric generators. That plant that you see in the distance there is producing electricity by using magnetic induction, basically. So magnetism it's not a rarity in our world. Far from it. It's ever present.
Visit the set of a major motion picture, and you'll see just how present it is.
Okay, so how's the car? We like the car?
Now you're sitting down, correct, Matthew?
No, I'm standing up.
You're standing up.
I'm standing up right now.
We have passed from the machine age to the information age. Another technological revolution brought to you by magnetism.
Another magnetic force happening. Whoa!
Get ready, please.
We are rolling.
Camera more.
Action.
Magnets in the camera motor move the film. Earphones have magnets that move little metal diaphragms to reproduce sound. The picture on the video monitor is painted by an electron beam controlled by a magnet. The computer stores its bits and bytes on a magnetic disk. A magnet in the record head stores audio information.
It's interesting to reflect on the fact that 1 teaspoonful of rust powder coated onto floppy disks and videotapes can store more information than all of the clay tablets in ancient Egypt.
Audio tape, computer disks, and video cassettes all store information magnetically. But data storage is not magnetism's only contribution to the information age. Electromagnetic waves enable us to transmit this data all over the world.
The most important single function of magnetism is that it can transport energy through the universe. We wouldn't feel the radiation from the sun if there weren't electromagnetic waves to transmit it.
Electric and magnetic fields that vibrate at right angles to each other create the waves that transport radio and television signals through space. Even light travels in the form of an electromagnetic wave.
So light is a vibration where the changing electric part induces a magnetic part, which induces the electric part, which induces the magnetic part, and the whole thing keeps inventing itself, moving outward in a line, and that's what's coming out of the sun. That's electromagnetism that's coming to us.
The unified force of electromagnetism that makes a motor run also transports the light and energy that sustains life on Earth. Magnetism has made our modern world possible. But the journey is not over.
Silence now. The race is about ready to begin.
Wait.
On your mark, get set, go. Ready, one.
When we ride into the 21st century, we may be doing it on a magnet. This is no ordinary train. It's a magnetic levitation vehicle known as maglev, a machine that uses magnets to fly. Put two north ends of a magnet together, and they're pushed apart. The force that propels a toy car can also lift a 50-ton maglev off its tracks. Strong magnets in the vehicle induce repelling forces in the aluminum track, just as your face is reflected in a mirror.
There's no interaction between a permanent magnet and the aluminum because aluminum is non-magnetic. But if this aluminum is moving, then it produces a very strong repulsion force on the aluminum. And that's because the magnet induces an image of itself in the aluminum, and it sees a magnet of like polarity. North pole sees a North Pole and repels.
So repelling magnets lift maglev 6 inches off its tracks. But what propels the vehicle forward? Attraction and repulsion. Alternating magnetic fields in the track interact with the vehicle to move the floating maglev forward at up to 300 miles an hour. If all this seems vaguely familiar, maybe it's because floating vehicles have been a staple of science fiction for decades. And real-life maglevs have been around as long. In New York in 1914, Émile Bachelet patented the very first maglev. It worked so well, it crashed through the wall of his laboratory. Since Bachelet, Henry Combe and others have perfected their own maglev designs. With vehicles already on track in Germany and Japan, Americans like Combe are waiting to see if their maglev will fly.
Magnetism has already revolutionized our society in many ways. It's waiting in the wings to do new things.
They're doing new things at MIT's Magnet Lab, using magnetism to create energy from water. If you split uranium atoms, some of their mass is converted into energy. Lots of energy. This is nuclear fission. You can also make energy by squeezing atoms together. Fuse 2 hydrogen atoms, and you get 1 helium atom, plus energy. This is nuclear fusion. At MIT, they're using magnets to create energy from fusion.
If you were to weigh the helium atom that you made and compare it to the weight of the 2 hydrogen atoms that went into the reaction, you'd find that the helium weighed just a little bit less. And that small difference in mass is converted to a huge amount of energy by the famous equation E equals mc squared. E is energy, m is the change in mass from 2 hydrogens to 1 helium, and c is a number which represents the speed of light, which is 186,000 miles per second. C squared is the speed of light multiplied by itself. It's an unimaginably huge number. So an extremely tiny difference in mass releases a tremendous amount of energy. And that's what fusion is.
And that's what keeps the sun burning. But if you captured a little bit of the sun, what could you keep it in? The answer is magnetism, a magnetic bottle. Steve Fairfax is chief engineer of MIT's plasma fusion reactor, the tokamak. He is keeper of the bottle.
We send the power for a medium-sized city through these 5-foot-thick concrete walls and on into the magnets of the tokamak, where we use them to produce a very powerful magnetic field. Inside the tokamak, we're going to heat a gas to 50 million degrees. Now, the center of the sun's only about 15 million degrees, and there's no material on the planet Earth that will withstand a temperature of even 1 million degrees. So we use all this power to make a magnetic field and create a magnetic bottle that holds the plasma away from the walls of the machine.
At MIT, they use 15,000 gallons of liquid nitrogen every day to cool their electromagnets to 350 degrees below zero. Once cooled, they can send huge pulses of energy through the magnets and into the tokamak.
The magnetic force is so great that it would lift a stack of cars as tall as Mount Everest, and it takes 100 bolts like this to keep the machine from flying apart.
Inside the machine's donut-shaped chamber, gases are heated until the atoms lose their electrons and the gas becomes a plasma. Because it's too hot to see inside the tokamak, Fairfax has a model that shows how magnetic fields are used to induce fusion.
Now, if I take this horseshoe magnet and put it next to the plasma, you can see that the magnetic field from this magnet is having a fairly strong effect on the plasma. It can move it around. Now, we don't use horseshoe magnets in our research. We use electromagnets like this. So when we turn that on now, you can see the plasma has clearly been squeezed away from the walls of the tube. Because it's not touching the tube anymore, the plasma's hotter. It's not being cooled off as much by touching the tube, and that's what makes it brighter. So this is the very same principle that we use in our machine, only where this plasma is a few thousand degrees. In our machine, we're shooting for temperatures of 50 million degrees.
The tokamak now requires more energy than it produces by fusion. But when they reach 50 million degrees, they will be one step closer to producing power to light the world. Power to replace fossil fuels. Cheap power.
It means that we will have a means to extract energy from seawater without causing pollution in the form of radioactive fuel elements that have to be disposed of. We will produce nothing but pure energy and light. That's the dream.
To understand the beginning of the world remains one of our greatest quests. How did this elegant and complex universe come to be? At Fermilab outside Chicago, they are using magnets to mimic the moments of creation. Here they discover magnetism is not just one of man's tools. The electromagnetic force itself is key to unraveling the mysteries of creation.
If you look from the top floor of this building, you see a large circle, which is 4 miles circumference, and particles go around that circle. Now, what do you think makes them go around the circle? I'll give you 26 guesses as to what makes particles go in a circle. Magnets.
Magnets forming the circular accelerator pull atomic particles around the 4-mile track 50,000 times per second. When these particles collide, it's a miniature Big Bang. From the debris emerges a picture of how the universe began.
At the Big Bang, we think the world was pristinely simple. One particle, one force, maybe the force and the particle were sort of the same. And then the universe, as it cooled, got more complicated.
Today in our universe, there are just 4 fundamental forces. Gravity. That's what keeps all planets and galaxies in place. The strong force holds atomic nuclei together. The weak force causes slow disintegration of atomic nuclei. The electromagnetic force binds electrons to nuclei and ties atoms together into molecules. The holy grail for physicists is a theory that would link all 4 forces.
Now, Einstein spent 30 years of his life trying to connect gravity, a primal force which keeps the Earth in its orbit around the sun and makes apples drop down off trees and things like that. Gravity and electromagnetism, try to combine them, unify them, without success. But the unification objective is still with us.
But scientists today have linked only 2 of the 4 forces.
Now, the weak and electromagnetic unification is something we've been able to replicate in the laboratories like Fermilab right here, because the weak and electromagnetic are representative of temperatures which we can produce artificially by collisions in our laboratory.
To achieve total unification, physicists would need an accelerator 1,000 light years around. Even if such an accelerator could be fashioned, no one knows what the benefit might be. But that's how it's always been with magnetism. From the compass to creation, this mysterious force lures us into a world of discovery.
All we can do now is say, look, it's important for humankind to know the world in which we live. We live in this world. How did we get here? What are the processes by which we got here? What is the future of the universe going to be like? The process of understanding magnetism created a vast opportunity for humans to live a better life.